Hello. Another example is static equilibrium problems. This is a very classic problem, comes in the guise of a wooden board, a bar, um, ladder. So there are several different variations of this problem, same problem, but you could have a person going up the ladder, so there would be another force on the ladder. But here we look at a very simple situation where a wooden plank of mass m and length L. Turns out L is not important in this problem, but let's say length L, and it is set against a vertical wall, and the angle that makes is theta. So we're supposed to get the forces, and this wall is frictionless. So it's important. I separated that out over here as a frictionless wall. So there is no friction across it. There's no force that direction on the ladder. So, okay. So first we need to identify the forces we need to find, and then set up equilibrium conditions, and then we find them. Okay. So that's the strategy. Let's look at forces that on this ladder. Well, I'm going to redraw it, so I have this original picture up there. All right. So redrawing. So you have a straight line here. Well, there will be the force of gravity right at the center of gravity. So halfway, this distance will be L over 2. That's where mg will act. Okay, now this force is pushing against this wall, so the wall will push back. So we expect normal force from the wall on the ladder, so we can write like that. So we need a notation for that. Maybe normal force from the wall, like that. Over here, this pressing against, as well as there's if there's no friction, this whole thing will slide down. So there is a friction that way. Let's call that F, and we can call this N, just N, or you want to N sub F, but for the consistency. But this is the static friction from the floor. Well, let's decorate it. Okay, so it seems like we need to find these three forces, the magnitudes of these forces, and we'll set it up if I'm very sure about the direction, but if we find their values to be negative, then I may have guessed it wrong. You may be wondering why the static friction is this way. Well, if you think about if there is no friction, then this ladder will kind of fall this way, fall further out. So ladder will move that way, right? So no friction. Oh, that will happen. So if there's a friction is opposing that. I hope this explanation makes sense to you. Okay, so this is the force picture, and the center of mass has no acceleration, and so we have conditions that there are two static conditions. One is a sum of all the forces, vector sum, is 0, and then the torque about any point, the net torque is 0, and so torque about any point, so just same notation, that's also 0, and these are all external forces. Okay, and this symbol means get a net. add them up. This is the same, add them up. So the torque, when you add them up, you have to also be cognizant of the fact that torque can be counterclockwise or clockwise in this situation. So one thing to notice is this: all these forces are in XY plane. They are all in this plane. So if I pick this as X and this as Y direction, the torque can be either in the Z direction or opposite Z direction. So I'm going to get only one torque equation. So this will be on one equation. Here, when you have a static equilibrium, the pivot is arbitrary pivot. So right away, I notice that if I pick this as the pivot and do the torque equation first, I will get NW right away, because these guys will not have any torque about this point, and this will have a torque and this will have a torque. They will have to balance. Pretty neat, right? So right away I can get one of the forces. So I try to see how much I can get from that first. That's my practice. But if I had picked this as the pivot, then I'll have a equation with these two as both unknowns. So, but picking this made it just this unknown. Let's work this out. So I'm going to do the two first. So this is the pivot point. Let's call this point A. Choosing A as the pivot. I got torque of NF is 0 and torque of Fs is 0, torque of mg. So I need mg times the lever arm. So lever arm is, you know this, so from here it drops. So mg is going down like that, and so I need, this is the point A, so this is my lever arm. So lever arm for mg. So that if this is theta and this is L over 2, so that's L over 2 cosine theta. So mg L over 2 cosine theta. Make sure you understand this, because this is if you make a mistake here, it's going to just go snowball and carry on, right? So I'm looking for adjacent here. So what helped me identify is that, you know, you take the line of force and from the pivot you drop the 90 degrees, and this is the lever arm for this force. How about the lever arm for that force? The only other force left, tau of NW, is going to be NW times the lever arm times, I need to get the lever arm. Well, I'll draw a picture just like that. I hope you draw a new picture every time you're working on the lever arm, because it can be very cluttered. I drew this and drew this, it's going to get very cluttered. So this is the force, horizontal. So I make it as big as necessary, and from here I drop a 90 degree on that. So that's the lever arm. So this is the lever arm for NW. So I need to figure out that distance. And this distance L and this is theta. Well, if this is theta, then this is theta too, because opposite, right? And from here, this is the opposite side of it, this triangle. This triangle. So I get that it actually is sine theta now. So this is L times sine theta. Okay, I have done with these lever arms. So can you erase this? This says add all of this in a vector way. So I need to have clockwise and counterclockwise. So this is clockwise and this will be counterclockwise. So this is counterclockwise and this is clockwise, which means if I take this as a positive, then this will be negative, and vice versa. So we just do it that way. So I have NW L sine theta minus mg L over 2 cosine theta equal to 0. Well, I can send this on the other side. So I get NW equal to L cancels out, mg cosine theta over sine theta. So this is the NW. So we got this guy. So how do I get these other guys? So well, I'm done with this equation because in the xy plane you're only going to get one of them. Now this is going to, one equation will be along the x-axis, one along the y-axis. So just look at the x component. So now I'm going to use these equations to see if I can get these guys. So if you look at just the x direction, this guy is x direction, this does not, this does not. So sum of fx equal to 0. This gives me fs minus nw equal to 0. Gives me fs minus nw equal to 0. And that means fs equals to nw. So I already got the nw, so if I have numerical values, I'll just have had some numerical value there, I'll have the same. So fs has to balance nw. Makes sense because they're the only horizontal component forces. Now how about the vertical component? Fy equal to 0. Well, the only vertical forces are this and weight, so they're going to have to balance. So Nf is going to be minus mg equal to 0. Thus Nf has to be mg, m times g. Okay, that completes the example. You can work out another problem just like this. You can give yourself a problem with some particular values of mass and g and mass and theta, something like that. So maybe try theta equals to 60 degrees. Okay. A variation of this problem is we found fs this, right? This is not necessarily the maximum fs. A variation of problem that's very interesting is as you make this ladder, make the angle some larger and larger, it becomes more stable, right? How about if I make the angle smaller? At what angle, some theta critical, and I give you mu s equals say 0.5 for this floor. So I want to find out what is the critical angle below which it just falls. That's a very good problem. Okay, so try to do that problem. You will see that in addition to these equations, you are also in that problem you're going to have a fs and nw and nf, because this will be max, because for the critical value you will be using max, so this will be actually not independent anymore. Unlike here, they will be related through mu s. Over here, these guys are independent because I wasn't using all of the friction that would be possible. I was using whatever friction is necessary, whatever friction is needed to balance all the other things that are going on. Okay, here just happens to be friction just balances NW. Okay. I hope you can do this other problem. I posed this problem in the video earlier. I just want to make sure that I put the answer there for you to check. So we are trying to find not at any angle, but at a critical angle when f is max. So if you look at the balance, you're going to get all of the same equations. So you will get NW is equal to this, same, and you're going to get Fs equals to Fs max, and that's going to be NW. So that's this stuff. and then you're going to get NF is equal to mg. So because this is Fs max, the ratio of that equals to mu sub s. So we will take a ratio of this, and Fs max over NF, and we'll set to mu s. So if I put this in here and put this in here, the mg cancels out, and so this gives me cosine theta over sine theta equals to 2 times mu s. Now this is a trigonometry called cotangent of theta, so that's equal to 2 mu s. So I can solve for theta, and that's a critical theta now, critical theta. So this critical theta is, theta critical is r cotangent of 2 times mu s. Now I picked a nice enough mu s is 0.5, so this becomes 1. So you have r cotangent versus 1. So you may remember the tangent is cotangent is tangent is this, right? P over B is tangent. So cotangent is B over P. So it is saying that this and this have to be equal. What's the angle at which this and this are equal? And that's it at 45 degrees. So anything less than 45 degrees under this condition, it will just slide down. So I'm going to stop here now. Hope this helps.